Oh, yeah. Assalamualaikum. Good afternoon. The topic today is drying of solid. This is based on English one of the book, chapter 33, page 1532, purpose of drawing. So, like its name, the removal of small amount of water, organic liquid from solid. So, the difference with evaporation. Evaporation will remove large amount of water, and evaporation water is removed as vapor at its boiling point. To drying is removed as a vapor by air. The moisture content of the final product varies depending upon the type of the product. Example, dried salt is 0.5% of water, 4%, the product of 5%. Drying or dehydration of biological material, especially food, is used as one of the preservation techniques. Or in the absence of water, below 10%, the microorganism is not active. But to preserve the flavor and nutrition, must be less than or equal to 500% water content. Some biological material and pharmaceutical may not be heated by ordinary drying. Maybe it is dry, like instant coffee. General drying methods are two methods, like batch and continuous. The type of physical condition heat is added by direct contact with heated air at atmospheric pressure. Vacuum drying and freeze drying. For vacuum drying, we have it in our lab now. Freeze drying, yes, we also have freeze drying in the lab. There are several types of dryers. The tray dryer, vacuum chef, indirect dryer, continuous tunnel dryer. All of this equipment is available in the book. Rotary drum spray dryer. This is tray dryer. So for this case, the tray contains the product we want to dry. So the air in is heated air. Oh, sorry. Air in is normal air. There's a heater here. And to circulate the air and air out. So for the tray dryer, this is the simplest all. In the case of Berliner material, the metal can be loaded on screen, which form the bottom of each tray. Then in this through circulation tray, dryer heated air passes through the permeable bed, yielding shorter drying time because of the greater surface area exposed to the air. We have a spray dryer. So for spray dryer, in a spray dryer, a liquid or slurry solution is sprayed into a hot gas stream in the form of a mist or of a fine droplet. So this normally we see in instant coffee. Nescafe have two methods. The red one is using spray dryer. The gold one, the spray gold is using a freeze dryer. So although the liquid is the same, it's a coffee, but the taste will be different. The water is rapidly vaporized from the dotted living particle of dry solid which are separated from the gas stream. The flow of gas in liquid in the spray chamber may be contact current, co-current, or combination. For this case, it's a co-current. Liquid coming from up, put in here, turn to solid, solid go down, the heated air go to the exhaust gas. Here there's a cyclone separator. Some of the solid will go through here to the hopper. Vapor pressure of water and humidity. This is the phase diagram for water. So along the line AB, A and B, this is the solid, liquid, vapor region. Along the line AB, the liquid and vapor phase coexist. Along this line, A and B. So that liquid or water, here you can say water. Is in liquid and solid, sorry, liquid and vapor phase. Along the line AC, is ice and liquid phase coexist. AD, the ice and vapor phase exists. So if ice at point 1 is heated at constant pressure, meaning the pressure is the same here, the temperature rises and the physical condition is measured as moving horizontally. So it can only move from solid to liquid then vapor. If the horizontal line crosses AC, solid melt and crossing AB, the liquid vaporize, moving from 3.3 to 4, the ice subline, meaning the solid goes straight to the vapor region. That one is the sublimation without going through the liquid phase. Liquid and vapor coexist in equilibrium along the line AB, which is the vapor pressure line for water. Boiling occurs when the vapor pressure of the water is equal to the total pressure above the water surface. So vapor pressure of the water is equal to the total pressure above the water surface. So for example, at 100 degrees C, the vapor pressure is 101 kilopascal, and therefore it will boil at 1 atm. So at 65.6 from the steam table in appendix A2, The vapor pressure of water is only 25.7 kilopascal. So hence 25 kilopascal is equal to water will boil. If a pan of water is held at 65.6 degrees C in a room at 101 kilopascal, the vapor pressure of water will again be 25.7. This illustrates an important property of vapor pressure of water, which is not influenced by the presence of an inert gas such as air. That is, the vapor pressure of water is associated with the gradient of the vapor pressure of the system. Okay. Right. Now we go to humidity. Wait a moment. Humidity. Uh, also for drying, it will directly related to humidity and the humidity chart. If you learn about cooling tower, operator, it also related to this. What else? Energy balance also related to this. So in under humidity, you have definition of humidity until humidity chart. Okay, whatever temperature. So what is humidity? So humidification involves the transfer of water from the liquid phase into a gaseous mixture of air and water vapor. Dehumidification involves the reverse transfer, whereby water vapor is transferred from the vapor state to the liquid state. In definition, humidity H of an air water vapor mixture is defined as the kg of water vapor contained in kg of dry air, which is the unit of humidity. Kg H2O slash kg dry air. Humidity depends on partial pressure PA of water vapor in the air and total pressure P is going to be 101 kilopascal, 1 atm or 760 mmHg. So the humidity is defined as question 9.3-1. So H equal to 18.02 over 28.97. This is pressure of water. Partial pressure of water divided by P pressure minus this partial pressure of water. Okay. So P here refer to total pressure. So for the total pressure P, this P, it's 1 atm or 760 mmHg or 101.325 kilopascal. It's atmospheric pressure lah. The saturated P. Water vapor is in equilibrium with liquid water at the given temperature and pressure. So for the saturation humidity, it's using PAS, which is vapor pressure of pure water at given temperature. Hence the saturation humidity HS is the same, just changing the partial pressure. So in this case, the partial pressure of water is equal to vapor pressure of the water. It's different. Next is the percentage humidity, HP, is 100 times the actual humidity H of the A divided by the humidity HS. If the air was saturated at the same temperature and pressure, so 100 H over HS. H is the humidity, HS is saturation humidity, then we get HP. Percentage relative humidity or HR, the amount of saturation of Na water vapor mixture is also given as percentage relative humidity HI using partial pressure. So HR equal to 100 PA referred to partial pressure divided by vapor pressure of water. So that HR is not equal to, now that HR is not equal to HP. HP is percentage humidity, HR is relative humidity, although both is percentage. So HP is based partial pressure by combining 30. Okay. Example. So the air in a room is at 26.7 degrees C. Pressure of 101.325 kPa. The pressure is equal to P. Wait. And contain water vapor with partial pressure of 2.76 kilopascal. Calculate the following: humidity, saturation humidity, surface humidity, and relative humidity. So from steam table appendix A2, in this book is mainly focusing water only. We have steam table, heat transfer properties of water, vapor pressure, latent heat. So from the steam table at 26.7 degrees C, the vapor pressure of water 26.7. Okay. The vapor pressure of water is 3.5 kilopascal. Also, PA equal to 2.76. The vapor pressure PA is referred to partial pressure, with P is 101, which is the ATM. For part A, using equation 9.3-1, just plug in, and we get 0.01742. So PA here refers to partial pressure. For part B, which is saturation humidity, this is using vapor pressure. So when you get vapor pressure from table A2, there's 2, from the A2, then you get 0.2226 kg. This is a unit for humidity, kg H2O per kg A. The better part is kg H2O over kg dry A. The percentage humidity from equation 9.3-3 is, so this is HP, 100 times H over HS. So HR is based on partial pressure and vapor pressure. So see here, the value for HP, HR is not the same. Huh? HP and HR is not the same. Dew point of an air water vapor mixture. The dew point or dew point temperature is the temperature at which a given mixture of air and water vapor would be saturated. Example from steam table at 26.7 degrees C, saturation vapor pressure PA is equal to 3.5 kilopascal. Hence, the dew point of a mixture containing water vapor having a vapor pressure of 3.5 kilopascal is 26.7. So if an air water vapor mixture is at 37.8 degrees C and contain water vapor P equal to 3.5 kPa, the mixture would not be saturated. It will be saturated at 26.7 degrees. Humid heat of an air water vapor mixture, the humid heat CS, we also refer to the book, it's the same. It's the amount of heat in joule or kilojoule required to raise the temperature of 1 kg of dry air plus the water vapor present by 1 Kelvin or 1 degree C. The heat capacity of air water vapor can be assumed constant over the temperature range usually considered at 1.005 kilojoule per kilogram dry air Kelvin and 1.88 kilojoule per kg water vapor Kelvin respectively. So this is referred to heat capacity of air and water vapor. Heat capacity. Terus mana ni? Okay, heat capacity of liquid. Liquid stimulus. Sudah. So hence for SI and English unit, so CS, which is humid heat, equal to 1.005 plus 1.88 H. This is SI unit. This is for the English unit. In some cases, CS will be given as 1.005 plus 1.88 H, 10 to the power of the 3. This is Joule Kelvin, Joule kg per Joule kg Kelvin. It's the same. It's for kilojoule. This is just Joule. Cubic volume of an air water vapor mixture, the cubic volume VH, is the total volume in meter cube of 1 kg of dry air plus the vapor equal to 101 kilopascal atm. Absolute pressure under given gas temperature using the ideal gas law. So VH equal to volume, permit volume, meter cube per kg dry air. So this is for SI unit. This one is for the English unit. For a saturated air water vapor mixture, H is equal to HS, and VH is the saturated volume. 7 total enthalpy of an air water vapor mixture. The total enthalpy of 1 kg of air plus its water vapor is HY in joule per kg or kilojoule per kg dry air. If T naught is the datum temperature chosen, datum referred to is equal. It's also called a reference temperature chosen for both component. The total enthalpy is the sensible heat of the air water vapor mixture plus the latent heat lambda naught Enjoy packaging and enjoy packaging of water after water vapor at T not at the same temperature. So HY order total enthalpy of KGA plus its water vapor HY is equal to CS multiply with T minus T not equal to the 15 temperature plus H lambda not is the latent heat or equal to 1.005 plus 1.88 H equal to humidity T minus latent temperature plus H lambda not. This is for the English. This is for the sorry, this is for XI. This is for the English unit. Now humidity chart. It's just introducing because in humidity there's a lot of definition. Humidity chart figure 9.3-2 or in the book you can refer to 33.3-2. It's same. A convenient chart. This chart. This chart. This is the humidity chart. Humidity chart, a convenient chart of the properties of a water vapor mixture at 180 and absolute pressure. In this figure, the humidity hash is plotted versus the actual temperature of the A water vapor mixture, dry bulb temperature. So this is the dry bulb temperature. This is the humidity, yeah. Y-axis the humidity hash. X-axis is the temperature. So the temperature here is called also known as dry bulb temperature. So we have wet bulb temperature. So the curve marked 100%, this is 100%, running upward to the right, menaik dan ke tepi, ke kanan. To give the saturation humidity HS, this is in this line, as a function of temperature in example 33.3-1, 33.3-1 yang tadi, for 26.7 degrees C, 26 is HS was calculated as 0.20 25 here. 26 should be somewhere here. If you draw this straight and it intercept the HS, draw until it meet here, intercept A. So this value is 0.02226 kg to upper area. The same as the calculation that made in example 9.1. 9.1. 9.3-1. Because in the new book it's example 33.3-1. Noting this point for 26.7 degrees C here, 26.7, and HS 0.226, it fall on the 100% saturation line. Any point below the saturation line represent unsaturated A water vapor. So this line, the last line, 100% line, is the saturation line. So any line below it is representing unsaturated A water vapor mixture. The curved line below the 100% saturation line and running upward to the right to the right represent unsaturated mixture of definite percentage humidity HP. So this here is HS as saturation 100%. So here this one is HP, percentage humidity. Going downward vertically from the saturation line at given temperature, the line between 100% saturation and zero humidity hash at the bottom horizontal line is divided evenly into 10 increments of 10% each. Oh, this line 10% each, except this one. All the percentage unity line HP mentioned and the saturation unity line HS. This is all HP, 100% is HS, can be calculated from the data for the vapor pressure of water. For example, 33.3-2 in the book. Here is 9.3-2. This is based on the whole book. Okay. Entering a dryer has a temperature, dry bulb temperature of 60 degrees C and a dew point of 26.7 degrees C. Using the humidity chart, determine the actual humidity H, percentage humidity H, humid heat CS, and humid volume VH in SI, in English unit. So the dew point of 26.7 degrees C is the temperature at which the given mixture is at 100% saturation. So at 26.7, 26.7, okay. This is 26.7, draw a straight line, uh, intersect the 100% and draw the horizontal line, and yes, horizontal line, and crosses the x-axis. So here you can get the H. So in this case, the H is equal to 0.0225 kg to upper kg dry. So this is the actual humidity of A at 60 degrees C. But yes, getting this point where H equal to 0.0225 and T equal to 60 degrees C on the chart, the percentage relative humidity is found to be 14%. So 60 degrees C here, what straight line. So this line, if you refer to this percentage humidity, Assuming we have a kita kena betul matrix cell. So this line is between 20 and 10%. So based on the book, at this point, it's actually a 14%. 14% HP. That one is hash HP. The another one is calculate the CS. So to calculate the CS using equation 33.3-6, CS equal to 1.005 plus 1.88 multiply with hash. In this case, hash is 0.0225. Then you get CS equal to 1.047 kilojoule per kg dry air Kelvin. It is for SI English unit. You need to refer to another equation, similar equation but different value for English unit. Next is the humid volume at 60 degrees C. That one refer to equation 33.3-7. VH equal to 2.83 ton. What's it called? Oh, this one. Yes. This is VH. So in this case, this is a H 60, okay, 60 plus 273. Thirty-three point three dash 7. Okay. So plus 273 because the temperature is in Kelvin. Refer to 33.3-7 in Kelvin. Temperature given by the equation is degree C. Exercise. Later you do this exercise. Problem 9.3-3, 9.3-4. This problem is using humidity chart to do it. Now, this adiabatic saturation temperature. Consider the process shown in figure 9.3-3. This one. So, the entering gas of an A water vapor mixture is contacted with spray of liquid water. So this is the spray of liquid water. Inlet entering gas is here. Here. Let's continue with spray of liquid water. The gas leave having a different humidity and temperature, and the process is adiabatic. The water is recirculated with some makeup water added. So the water here is circulated back and plus makeup H2O. So the hash, the here inlet gas with humidity hash, temperature T, then come out at saturated humidity, saturated temperature. So the temperature of water being recirculated reaches a steady state temperature called the adiabatic saturation temperature Ts. This one, Ts. So Ts here causing outlet gas to be Ts as well, or saturation temperature. If the entering gas as temperature T having humidity H is not saturated, Ts will be lower than T. If the contact between the entering gas and the spray of the droplet is enough to bring the gas and liquid equilibrium, the A leaving is rated at Ts and has the humidity of HS. Right? Question. So in the book, page 1547, there are two equations. So for equation 33.3-11, that one is a relation between CS and H. Hmm. Example 33.3-3 or 9.3-3. An air strip at 87.8 degrees C, having a humidity H equal to 0.03 kg H2O per kg dry A, is contacted in an adiabatic saturator with water. It is cooled and humidified to 90% saturation. What are the final values of H and T? Second question is for 100% saturation, what will be the values of H and T? So for solution part A, the point H equal to 0.03 and T equal to 87.8 is located on the humidity chart. Okay. So 0.03. So this is 0.03 and 87.8. 87.8 will be here. We create a line from here. Here. The magnetic saturation curve through this point is follow upward to the left until it intersect the 90% line at 42.5 degrees C and H equal to 0.3. So from here is, so this line is actually an adiabatic saturation line. This line. So if you follow this line until it reach 90%, which is here, if you draw downward, you get 42.5. Here you get 0.05 kg H2O per kg dry E. So for part B, 100% saturation, what will be the value of H and T? So for the same line, it follow until 100%. So from here, 100%, 100% is here. So at 100%, the temperature is 40 degrees C, 40.5 to 40 degrees C. While the humidity is slightly higher, 0.0505 kg H2O per kg dry E. That is for the example 33.2-3. Next is the wet bulb temperature. The adiabatic saturation temperature is the steady state temperature attained when a large amount of water is contacted by the entering gas. The wet bulb temperature is the steady state non-equilibrium temperature reached when a small amount of water is contacted under adiabatic condition by a continuous stream of gas. Since the amount of liquid is small, the temperature and humidity of the gas are not changed, contrary to the case of adiabatic saturation, where the temperature and humidity of the gas are changed. So this is a wet bulb temperature. So for the wet bulb temperature, this is the thermometer. So to get the wet bulb temperature, the the thermometer must be soaked in water. Then you get the wet bulb temperature. If there is no water inside here, so we call it a dry bulb temperature. So this container or wick is so that wick is wet. So the method used to measure the wet bulb temperature. What is wet bulb temperature? So wet bulb temperature is defined as the steady state non-equilibrium temperature reached when a small amount of water is contacted under adiabatic condition by a continuous stream of gas. Since the amount of liquid is small, the temperature and humidity of the gas does not change, contrary to the case of adiabatic saturation, where the temperature and humidity of the gas are changed. So to measure the wet bulb temperature, we use this method, wick or cloth. The wick is kept wet by water and is immersed in a flowing stream of a water vapor having temperature of T, so T refer to dry bulb temperature and humidity H. At steady state, water is evaporating to the gas stream. The wick and water are cooled to TW. And stay at this constant temperature, the latent heat of evaporation is exactly balanced by the convective heat flowing from the gas stream at T to the wick at lower temperature TW. The heat balance on the wick can be met. The datum temperature is taken at TW, so T naught is TW. The amount of heat lost by vaporization, neglecting the small sensible heat change of the vaporized liquid evaporation is the equation. Oh, the equation juga. This equation Q equal to FA and A lambda WA. Panjang equation dia. Okay, that is what bulb temperature. Example, a water vapor A mixture having a dry bulb temperature of T equal to 60 degrees C is passed over a wet bulb as shown in figure 33.3-4, this figure. And the wet bulb temperature obtained is TW equal to 39.5 degrees C. What is the humidity of the mixture? So the wet bulb temperature 25.9 degrees C, 29.5 degrees C can be assumed to be the same as adiabatic saturation temperature T as we discussed following the adiabatic saturation curve at 39.5 degrees C until it reached the dry bulb temperature of 60 degrees C. The humidity is H equal to, okay. So 29 point here, 29. Oh, this is okay. So 29.9, 29.5 kan? Dekat-dekat 30 lah. Follow the adiabatic saturation curve of 39.9 until it reach the dry bulb temperature of 60 degrees C. Mm, 0.013125. should be like this. Okay. One of it, the advertising of the brand different. Macam ni lah, hello, macam macam baik. Ni kalau macam tu. Aduh. So at 60 degrees C, so 29.9 is here. Okay, 29.5. Untuk 30 lah. 60 degrees C. Let's see what. Yeah, okay. Follow this. Separation curve. Then you get the 0.0135. Yeah, actually, but this is how it's done. Okay. Now it's equilibrium mixture content of the material. This is based on experimental data. 9.4 dash 33.4-1. This one is typical equilibrium mixture content of some solid at approximately 25 degrees C. Okay. So we have many material from paper to cotton, number 12. So typical, if the material contain more moisture than its equilibrium value in contact with a gas of a given humidity and temperature, it will dry until it reach its equilibrium value. If the material contains less moisture than its equilibrium value, it will absorb water until it reach its equilibrium value. For A having 0% humidity, the equilibrium moisture value of all material is 0. The equilibrium moisture content varies greatly with the type of material for any given percent relative humidity as shown in figure 23.4-1 for some typical material at room temperature. So non-porous insoluble solid tend to have equilibrium moisture content that are quite low, as shown by glass wool, number 11. 11, yeah. This one. 11, itu. Then and kaolin is 6. Right, kaolin is 6. Okay. Certain spongy cellular material, organic, biological, and logical region used to large variables to contain. This one we can see in wool, leather, and wood. The same one is leaf, leaf, wool. Wool, number 2. So how to use this? Let's say for 5. 5 is later 10. Let's say at 60% relative humidity. So from here, you can actually get the equilibrium water content of a pipe. 60% HR, we get around 17, yeah, 17 maybe kg H2O per 100 kg dry solid. So meaning in that sample, there are 17 kg of water inside per 100 kg of dry solid. So if you have a 100 kg of leather, so inside that 100 kg of leather, there exists 17 kg of water that is based on HR 60%. So the lower the HR, the lesser the water content. This is for food. Now is the rate of drying curve. Of drying curve. Introduction and experimental method. Okay, and the rate of drying curve. This is the section, subsection, or subtopic that will be covered. To determine rate of drying for a given material, a sample is usually placed on a tray. If it is a solid material, it should fill the tray so that only the top surface is exposed to the drying air stream. By suspending the tray from a balance in a cabinet or duct through which the air is flowing, the loss in weight of moisture during drying can be determined at different intervals without interrupting the operation. So rate of drying curve for constant drying condition and from a batch drying experiment are usually obtained as W total weight of the wet solid, dry solid plus moisture active and time T was in the drying period. This data can be converted to rate of drying data in the following way. First, the data we calculated xt equal to W minus Ws over Ws, which is kg total water over kg dry solid. In this case, W refers to the weight of the wet solid in kg total water plus dry solid, and Ws is the weight of the dry solid in kg. The free moisture content X in kg free water per kg dry solid is calculated for each value of xt. So xt, t here refers to time. So at certain time, there's a different value of x. Where x star, the equilibrium moisture content kg equilibrium moisture per kg dry solid can be determined for the given constant drying condition. Using the data calculated from equation 9.5-2, a plot of free moisture content X versus time t in our is met as in figure 9.5-1e. So 9.5 dash 1A, this is the X versus T. X is the free moisture content. To obtain the rate of drying curve from this plot, the slope of the tangent drawn to the curve in figure 9.51a, this figure, can be measured, which give value dx over dt at given value of t. So what does it mean for obtaining R? So what does it mean is at certain time period, if you want to know the value of dx over dt, or the slope, ya betul lah, dx over dt, you just do the tangent. Tangent means let's say this point. So tangent is something that can just pass through that point, something like this now. Then you calculate this slope lah. Satu. So for obtaining R, a value of Ls over A of 21.5 kg per meter square was used. So Ls over A for this graph is 21.5. The value is fixed. So R drying rate equal to negative Ls over A dx over dt, where R is the drying rate in kg H2O per hour meter square, and S is the kg of dry solid used. A is the exposed surface area in meter square. So drying rate curve is then obtained by plotting R versus moisture content X. So once you calculate R, then you can plot R versus X. This is how the graph look like. It started from A, not E. A, B, C, D, then E. So at point A, for both graph, A and B, at 0 time, the initial free moisture content in the beginning, the solid is usually at a colder temperature than its ultimate temperature, and the evaporation rate will increase. A is here, bawah sikit. Next is the surface temperature rises to its equilibrium value. Alternatively, if the solid is quite hot to start with, the rate may start at point A, A prime. A prime. So if it's A here, because it's cold, and heat it up using heated A, it slowly go up and reach the equilibrium. If the sample started at temperature above the equilibrium temperature, or the system, the drier temperature, is start here. And from point B to point C, B to C is the constant rate period. The slope and rate are constant during this period. This constant rate period is shown as line BC. So its drying rate is constant. At point C on both plot, the drying rate start to decrease in the falling rate period. This is the falling rate period. So the drying rate is reducing. This is better because it's higher. This is become lower until it reach the point D. Point D. In this first falling rate period, the rate shown as line CD in figure 9.51b, this figure, is often linear. So this linear often linear. At point C in 9.51b is the critical free moisture content axis. So this point, point C, this point C, this is constant period, end of constant period. So it's the end of constant period, which is point C, which is called critical free moisture content. The entire surface is no longer wetted. So the wetted area continues decrease in this first following period until the surface is completely dry at point D. At point D, the rate of drying fall even more rapidly until it reach point E. Dan makin rendah. The equilibrium masih contain is X star, and X equal to X star minus X star is equal to 0. The one is point E. Okay, calculation method for constant rate drying period. The important factor in drying calculation is the length of time required to dry the material from a given initial free moisture content X1 to a final moisture content X2. Two methods. First method is method A, using experimental drying curve, using the drying curve. The second one is using rate of drying curve for constant rate period. Method B is method using predicted transfer coefficient for constant rate period. So method A using the experimental drying curve, example 9.6-1. Example 9.6-1. Okay. Example 9.6-1, a solid whose drying curve is represented by figure 33.5-1a or 9.5-1a is to be dried from a free moisture content X1 equal to 0.38 kg H2O per kg dry solid to X2 0.25 kg H2O per kg dry solid. Estimate the time required. So this one just 1.28. This is the red line referred to 0.38. X2 blue line is 0.25. Here is the time. Just subtract it. Then we get 1.8 hours. Next method is using rate of drying curve, R equal to negative NSA f dx over dt. The equation can be rearranged integrated over time to interval from drying from x1 at t equal to 0 and x2 is t equal to 2. Then if you integrate it, t is t minus 0 is t equal to ns over arc x1 minus x2. Similar question, but using different method. This is using rate of drying curve. Method yes, rate of drying curve for a constant rate period. So LS over A value is 21.5. This is LS. Oh, So from figure 9.5-1b, this is using R versus X. So to get RC, you need to get the value from the constant rate period. Passes through y-axis drawing rate R. This one is 1.51 kg to per hour meter square. Substituting into equation 9.6-2, this equation 21.5, this is equal to LS over A divided by RC. This is the 0.38 minus 0.25. The answer is 1.85 hour. This is very close to 1.8 hour in example 9.6-1. So 9.6-1 is using dry curve. Next method is using predicted transfer coefficient for constant rate period. So equation for predicting constant rate period, the rate of convective heat transfer Q in watt joule per second or BTU per hour from the gas at T degree C to the surface of a solid TW degree C where T minus TW equal to T minus TW Kelvin. Sama lah. So Q equal to HT minus TW. A is the exposed flaring area. H is the heat transfer coefficient in watt per meter square Kelvin. So the equation for the flux of water vapor from the surface is NE equal to KYYW minus Y. The amount of heat needed to vaporize NA kg mole per second meter square. Water is Q equal to NA lambda WA. Lambda W is the latent heat. Okay, latent heat we can refer to appendix A2 water. Rate of drying RC. Last time RC is based on figure. Now we calculate RC. So RC equal to H over lambda W. Lambda W is latent heat. Latent heat we can get value at appendix A2 T minus TW multiply with 3600. What is for SI? The heat transfer coefficient can be calculated as follows. H equal to 0.0204 G, 0.8. That one is SI, where G is equal to V rho, and H is, unit H is watt per meter per Kelvin. V is velocity, rho is density. Time of drying during the constant rate period. So T equal to LS lambda W x1 minus x2 over AH2 minus TW. Equal to 9.6-11. Let's see. This is based on the method, another method B. The first method is using graph, drying curve, or rate of drying curve for constant rate period. Now it's using prediction of constant rate drying. So an insoluble wet granular material is dry in a pen 0.457 times 10⁵ meter. 1.5 multiply 1.5 feet and 2.5.4 millimeter deep. The material is 25.4 millimeter deep in the pan. The side and bottom can be considered to be insulated. Heat transfer is by convection from an A stream flowing parallel to the surface of the velocity 6.1 meter per second. The A is at 65.6, so this is the width of A. It has indeed 8.01 kg/H2O per kg dry air. Estimate the rate of drying for the constant rate period using SI unit or English unit. So for the humidity curve, sorry, from the humidity curve hash 0.01 and dry bulb temperature 65.5 using the humidity chart. The wet bulb temperature TW is found at 29.9. So it's here 29.9 with hash W is here 0.026. By following the identical saturation line, the same as the wet bulb line for the saturated humidity. Using question 9.3-7 to calculate the V hash unit volume. Remember, T here is in Kelvin, that's why it's add, you need to add 273. Yeah? So V hash is 0.974 meter cube per kg dry air. In this case, hash is equal to 0.01. Density for 1 kg dry air plus 0.01 kg H2O is this. Okay. The mass velocity G is 0, 6.1 meter per second. 3600, 1.027 refer to this density. Equation 9.6-9 hash. Then we calculate for hash 0.020 for G. G is from here. We get 68.45 watt per meter square Kelvin. So at wet bulb temperature 28.9, so lambda W latent heat at 28.9. One refer to steam table. 28.9. You need to do the interpolation to get 2433. Yeah? Jadi apa? Nice. Late. Ultimately use the steam table to get this value latent heat. Yeah? Substituting into equation 9.6-8 and noting that 65.6 minus 38.9 is 65 is equal to 65.6 29.9 Kelvin sama. So RC equal to this equation, H 62.45, latent heat 2433, T is 65.6. Inlet, yes, inlet A, minus 28.9 TW with bulb. Where do we get with bulb? From the humidity chart. Divided to 600, we get 3.39 kg per hour meter square. Then total evaporation rate for surface area of 0.457 times 457 meter square is RC multiplied with A. then we get 0.708 kg H2O per hour. So this is the total evaporation rate for this surface area per hour. Berapa banyak? Si banyak pun 700 gram water per hour. Next is that one is the constant rate period. So the constant rate period is referred to this one, in which the rate of drying rate is equilibrium. This is what we call constant rate period. This is the falling rate. It changes with time. Next is the calculation method for falling rate drying period. So for falling rate drying period, this one is buat numerical integration. In the falling rate drying period, the rate of drying R is not constant but decreases when drying proceed past the critical free moisture content Xc. The time of drying for any region between X1 and X2 has been given by Ns over E, X1 to X2 dx over R in falling rate drying period R varies, which is true. Yeah, the R varies at the moisture content by time. Or this one is based on X is free moisture content. So plot 1 over R versus X, determining the area under the curve using numerical integration. Example, a batch of wet solid whose drying rate curve is represented by figure 33.5-1b. 3.5-1b is to be dried from a sea moisture content of 0.38 kg to X2.04 kg H2O. The weight of the dry solid is LS399 kg dry solid, A equal to 18.58 meters square of top drying surface. Calculate the time for drying. Note that LS over A is equal to 21.5. Kalau bahagi. So from figure 33.5-1b, 33.5-1b, you can refer to page 1558, 1558 dalam buku. So the critical free moisture content or Xc is equal to 0.195 kg H2O per kg dry solid, hence the drying occurs in the constant rate and falling rate period. So this is the starting for the falling rate period and end for the constant rate period. For the constant rate period X1.38 and X2, Xc equal to 0.195 for figure 33.5. So from 38 to Xc, so in at 38, the period is still constant rate drying period. So we use equation 33.6-2, equation tadi. We get T 63H. The same equation. That one is for the constant rate period. Now is from 0.195 until 0.004. That one is referred to the falling rate period. So to determine this area by numerical notation using a spreadsheet, the equation are given in the following table. So starting from Xc to X, 2. This is the R, 1 over R. Where you get R? Write down graph lah. Graph. R, this is delta X, 1 over R average. So delta X multiply 1 over R average, you get 0.1889. Sekejap. Ada. For the following red period, reading value of R from various value of X from figure 33.1. 33.5-1b, the following table is prepared. Okay. Area of the first rectangle is the average height 0.663 plus 0.826 divided by 2 or 0.745 times the width delta X 0.195 minus 0.15 or 0.045 giving 0.0335. Other values are similarly calculated, giving a total 0.1889. So to get 1 over R, you use 0.663 plus 0.825 over 2. And to get delta X times the width delta X, 0 delta X 0.15 minus 0.115. Okay. It's apa? Oh, 0.195 minus 0.15. The X. Wow, cepatnya. Setting integration 33.6-1 equal to LS and A is 21.5 lah. In this case, dia bagi dah nilai 3399 nya. 18.58. Then for this numerical integration, value dia ialah 0.1889 equal to 4.06. Total time is 2.63 plus 4.06. This is the total time of 6.69 hours. This total time is from the constant red period to the falling red period. Oh, this stuff. So that's all for the drying topic. Could be the last topic for this semester. Later, maybe we can do during the study week, one class for revision. Thank you. Hope to see you.